Hello, welcome to a Lab 2 walkthrough. Okay, I'll try to make this super fast so you can spend most of your time actually coding and just go over the essential stuff. This is how you install the packages. Here's all the stuff you need to import. Okay, you need to make sure that you have a GPU available to you. If you're using Google Colabs, you can go to runtime and then change runtime to request a GPU or a TPU. But you need to make sure that you have a GPU. Well, you could do it without one and run everything on the CPU, and it will just take forever. And I mean like forever. Okay, so I want to work kind of from the big picture down to the little details. Even though implementation-wise, it's probably more straightforward to go from the little details and working your way up. But just, conceptually, I want to work our way down instead of up. Okay, so we're going to start with what is training a model? Well, it's just running a for loop and for a certain number of epochs, right? So we have this number of epochs, which is 100. And until we reach that number, we're going to train, right? Okay, well, what the heck is training? Well, training is when you go through the entire data set and learn everything you can from it. So we'll say for x and y truth in train loader we're going to learn. So for all of the explanatory variables and the actual variables in our data set, we're going to learn. Okay, so the first thing we want to do is put these variables onto the GPU. So we're going to say x and y truth equal x dot CUDA and y truth dot CUDA. And that will put them on the GPU. So sometimes the bus between the CPU and the GPU will be the ultimate bottleneck. Sometimes it's the GPU that's a bottleneck, sometimes it's the CPU, but very frequently it's the bus between those two. And so in order to speed that up, we're just going to make async equal true. And that will mean that, the Python code will go on to doing the next stuff, even if not all of the data has been put on the GPU yet. We need to get an optimizer. An optimizer is the thing that actually takes the step and changes the model, right? So everything else is just calculating what step we should make to change the model to be better. The optimizer is the thing that actually takes that step. The optimizer that we're going to be using, it comes from optim, and we're going to use SGD. Now, because this is the thing that actually updates the model parameters, we're going to pass those in so that it has a reference to them and it can change it later. And we're going to set the learning rate, and we will set it to 1 times 10 to the minus 4. So 1,000th, or is that 1/10,000th? Something like that. One of those two. Anyway, so after the first iteration, the optimizer is going to have all these, all the information from the gradient on the last iteration in it. And so we want to zero out that gradient. So we say optimizer dot zero grad. Now, we're going to do this every time, every iteration, but you could, let the gradient accumulate for multiple iterations and then do it like, say, once every 25 iterations or something like that. And you might want to do that if your batch if the batch size that you want to use is larger than what you can fit on your GPU. But we're going to skip that complexity for now and just say we're going to zero out the gradient every single time. Okay, so now we have X truth and Y truth. Before we can even know whether we're doing good or bad, we need to get a guess or an estimate. And we're going to call that Y hat. And Y hat is, it's the prediction that we made. So we're going to set Y hat equal to the model applied on X. The wonderful thing about Torch is that even though this is an object, it has a run function, and so you can run the object as though it were a function, right? And so X is the input image, and we're going to run the model on X. Again, this is a class, but we're running it as though it were a function. And so that's how we get our prediction. The next thing we need to do is figure out how bad we did. Was that a good prediction or a bad prediction? And so we're going to say the loss is equal to some objective function. And that objective function is going to take in Y hat and Y truth. Okay. Objective is not defined right now. And there's lots of different objectives that you could use. For example, there's the mean squared error, which, might sort of make sense because we're predicting numbers, but, in reality, this is more of a classification problem. And there's lots of different objectives that you could go for, lots of different loss functions. The one we're going to use is cross entropy loss. Okay, so the objective is defined here. We're using it right here. The last thing that we need to do is say loss dot backward optimizer dot step. Okay, this is a really tricky thing because loss dot backward is where we're computing the gradient, and optimizer dot step is where we're taking our step based on that gradient we computed. How the heck did optimizer know what loss computed? Where on earth is it getting that from? And here's the answer. Loss, all it did was call the backward function on everything that it was connected to, right? And it was connected to Y hat and Y truth. So it called the backwards function on Y hat. Y hat called its backward function, which was the output of this model X. And so every layer in the model called its backward function. And so each layer stores its own gradient. And now the optimizer, remember, we gave all of the parameters to the optimizer right here. And so what that means is the optimizer knows exactly what the gradient is, and therefore it can take the step. You don't have to pass the loss into the optimizer when you call dot step or anything like that. It just automatically knows. Okay, and this is everything you need to know about training. But right now we can't really evaluate whether we're training properly or not. So we're going to add some things in. First of all, we want to validate whether or not we did a good job. And so what we're going to do is right here, after we compute the loss, we're going to say if the epoch is a multiple of 25 and we are in the first batch of that epoch, then we're going to validate that the learning we're doing is on track. So we're going to have an array called train losses at some counter equals loss. Forgive my horrible style. Okay, so let's define those things up here. We'll say counter equals 0, train losses equals an array of none times 40. Okay. Or something like that. We'll think about what that's supposed to be later. So that's going to be our train losses. And we're going to say validation losses equals the same thing, times 40. Okay, so at the counter, we're going to add that loss. And then we're gonna do this exact same loop that we did here inside of this if statement, but we're gonna do it on the validation set instead. So we'll say validation X and validation Y, truth, in validation loader. For every value in there, we're going to say validation X and validation Y, truth equals themselves, but we're going to slap them on the CUDA. We're not going to zero out the gradient, and the reason why is because for the validation set, you don't calculate the loss and call loss.backwards. Why? Because you're not training on it, you're validating on it. The validation Y hat equals the model on validation X. And validation loss list dot append the objective function validation Y hat, which is our prediction, against validation Y truth. The objective function is going to evaluate based on the validation set as well. And instead of storing it in a loss and saying loss.backwards, we're just going to put it in this list. Then outside of the for loop, but still inside of the if statement, validation losses at the counter, so at the same index as we did before, equals the sum of the entire list divided by the length of that list. We want to increment the counter because we don't want to be inputting into the same index every single time that we validate. So now we have validation information on whether we're actually, doing good or not. So let's exit this if statement, and right here we can output some of the information that we've learned. So we can say loop.set description. We're going to say, the loss is 4 decimals of accuracy dot format loss dot item. So remember, loss is a torch tensor type thing. And so if you just want the number instead of the torch tensor, you have to say dot item. Otherwise, it's a zero-dimensional tensor that has one item in it. Okay, and then, you know what, I'm going to add to this. Let's also say validation loss equals the same setup, and then right here we're going to format it with validation losses at -1, and if I'm not mistaken, that's Python for the last element. So that will set, so even though we haven't finished the entire loop, it'll start giving us output right away because of this. And what it will tell us is what the current training loss is and what the current validation loss is. And then we will increase the batch number because we're not on batch 0 forever. Oh, yeah, right here we should probably say what batch we're on. Let's put that in here too. What is it for int? Is it just D? If that's not D, well, I apologize. Once we're done with training and everything, we'll say loop.close. Okay, that's the big picture. Now we have to go through and fill in all of the details because this is definitely not ready to train. First of all, what the heck is train loader? We never specified that. What the heck is validation loader? I wanted to, you know, just throw this out there, like, here's the big picture. This is, you know, our main function, but like, what are the details? Well, let's go define the details. Oh, and yeah, and then the other thing is, what the heck is our model? Where is our model? Ah, right here. What the heck is that? Where did we define that? Who says what that is? Well, we have to define that. So let's start with defining the model, and then we'll talk about the validation loader. In Torch, all models inherit from nn.module. Let's give this thing a name. So it's inheriting from nn.module. Let's call it a linear network. Okay, the first thing we need to do is define the init function, which will be called when it's created. Init always takes self, and we'll also give it the data set because the data set might have useful information. The first thing we're going to do in init is call the superclass, and we're going to pass into the superclass the class itself, and we're going to call its init function. Okay, now what this is doing is it's just letting the superclass know that this class exists, and, like, you know, to pass everything down when it can, and to get all of the parameters attached to this class to also be attached to the superclass. And I'm not really sure everything else, but I do know it's super important. You shouldn't mess that up. So we'll say x and y equals the data set at 0. We're just grabbing a random item in the data set. The specific item isn't important. I could do item 5. Now we're going to say, we're going to need to know the number of channels, the height, and the width in an image. And because we'll make our model based on that. And so we'll set these things equal to x.size. You can look that up. It's a torch function. It just returns exactly what you would think, the channels, the height, and the width. Now the out dimensions, you would think it's y, but y is a number between 0 and 9, which is the label of the digit that we're looking at. And so I'm just going to hard code in the answer. It's 10. Okay, so those are the important things we should know. Now let's actually make the network. So self.net equals nn.sequential. A sequential is exactly what you would think it is. It's a module that allows you to stack all of the modules within it in an order so that you pass them one by one. And you would think, oh, well, yeah, well, duh, like, isn't that what you always want to do? And so why would we do anything but a sequential? And it turns out there's lots of interesting reasons why you might not want to do something in a sequential way, and we will learn about that later in the semester. But for now, we're going to do this sequential. So its constructor is any number of arguments. And again, it really just, you know, however many you want, lay them in, and that's how a sequential works. Okay, so the ones that we want is we're going to have a linear layer. A linear layer is also called sometimes a fully connected layer. And then after that, we will have a ReLU. The reason why we need a ReLU is because a linear layer is essentially just a matrix multiplication. And if any of you have taken linear algebra, you know that multiplying a vector by two matrices is the same thing as multiplying the two matrices together and then multiplying it by the vector. In other words, two linear layers right next to each other is totally redundant. You have to have some sort of non-linearity between them to make the different matrices actually function. We're going to have a linear layer, then our non-linearity will be the ReLU, and then another linear layer. Now the parameters we're going to pass into this is the number of inputs. So C times H times W, that's the input. The number of channels times the number of the height, and then the width, right? Multiply all of those, that's the input. And then we'll just do a random number like 1,000. That's going to be the output of our linear layer. We're going to ReLU that output and then stick it through another linear layer. And we'll do another 1,000. I don't know the size of this matrix. Well, it's C times H times W times 1,000. This one is going to take as input 1,000, and as output, it's going to have, I don't know, whatever the out dimension is. Oh, well, out dimension is 10 because there's 10 classes. So this one is going to be a giant matrix 1,000 by 10. Okay, so that's our entire network. There are two other functions that we have to define. Well, two other functions you have to know about. One of them we have to define. First one is called the forward function. It does what you think. It passes things forward. Down here, when we say model on X, it's calling a Python function that will then call forward. It essentially passes it straight to forward. We could override the other Python function. The people who designed Torch thought it would be more intuitive to override a forward function and not a forward function, a forward function. So what the heck does a forward function even do? It really just returns self.net on X. That's essentially what it does. And why does it do that? Well, because remember, self.net is an nn.module, right? So it also has a forward function. This is your entire model. And so it seems a little bit ridiculous that we're nesting it inside of another model that will literally just call its forward function as well. But there's a particular reason why we're doing this. And the reason why is because this thing, this X, is coming in as a channel by height by width image. But the problem is that that's like a three-dimensional tensor. Now I've included n here. That's the batch number. When you include n, you suddenly realize, oh, this is actually a four-dimensional tensor. You can't multiply that by a two-dimensional matrix, which is essentially what a linear layer is doing. And so in order to get by, we have to flatten it. So we'll have a flattened version of X, and that will be equal to x dot view n by c times h times w. Now, what this essentially does is it smashes all of the dimensions together except for the batch size. So now we have a series of vectors, and since we have n vectors, we have the batch size number of vectors. We really just have a matrix. And you can multiply two matrices together, and that's exactly what we want, is this linear layer, which is a matrix, to be multiplied by this matrix, which is one data sample. Every column is a data sample, and all of those columns together is a batch, right? We're not running self.net on X. We're running it on the flattened version of X. Okay, so that's the forward function. The other function that you need to know about is the backwards function. And the thing that you need to know about backwards is to never touch it. Don't do anything with it ever. Backwards is the function that they call in order to calculate the gradient. Theoretically, maybe you want to overwrite that and calculate the gradient your own way, which you think is even better. But, you know, trust the mathematicians. They're pretty good at calculus, and they already have a great function set up for calculating backpropagation. Okay, so then the next thing we need to talk about is, okay, we have this model defined, but we were still talking about this train loader and this validation loader. Like, where the heck did those come from? So we're going to teach you how to create a test set. And we're going to call ours the fashion MNIST processed data set. It inherits from data set. Remember, this data set was defined right here. Again, the first thing we need to do is the initialization function. We're going to take self. We're going to take a root directory where we will save the data. And we're going to say that train equals true. We'll talk about that variable in a second. Self.data equals data sets dot fashion MNIST. Now again, we're really just creating a wrapper for a data set that somebody else created. But we want you to do this because, you know, at some point you're going to be dealing, in this semester even, you're going to be dealing with a data set potentially that you created, right? And so you can't just, you know, use a data set that somebody else created. You have to actually go through the init process and everything like that. And so that's why we want you to know how to do it by creating this wrapper. Okay, but if you look up datasets.fashionMNIST in the documentation, if you searched it right here, we're not going to, you would find that it takes a bunch of parameters, and the first one is the directory that it wants to save things in. We're going to say train equals train, which is true. Transform equals transforms dot to tensor. Download equals true. Okay, this is a transform that you can use to, you know, augment the data if you want to. The wonderful thing about transforms is there's a transform that lets you make a sequence of other transforms. And so if you wanted to, say, randomly rotate a bunch of the images 15 degrees and then turn it into a tensor, you could do that. But, you know, all we really want to do is transform it to a tensor. And so that's what we're doing here. And then download equals true. We're not going to talk to the server every time. We just want to download it, and we'll store it in root, which is the file path. Okay, the next thing that we want to talk about is the function getItem. GetItem takes in self and I. If any of you are new to Python, I'll give you a hint. If there's a double underscore before and after a function name, then it probably is a Python defined function and not a library specific function. And that's the case with getItem and init as well. GetItem overrides the access operator. So we're going to say x, y equals self.data. Again, we're just wrapping the data set that somebody else gave to us, but you know, if you were doing this yourself, you'd have to put in more logic. Okay, so that's get item. The other thing we need is length. So what we're going to do here is just return the length of self.data. This length function is the same thing as this length function. When you want to overwrite it, you do the double underscores. But you know, if you wanted to like decrease the size of your data, say you only really wanted to study the first 100 elements, then you could put 100 here instead, and then it would cut off the training at 100 elements. But we don't want to do that. We want to train on the entire thing. And so we're going to put the length of self.data. Okay, so now we have these classes, but those are just classes. They aren't these variables, so what the heck? Well, we're going to create some variables. Train data set is an instance of fashion mnist process, and the directory that we're going to keep it in is temp/fashion mnist. And we're going to say train equals true. We don't really have to do that because that's the default value. But now we're going to copy this entire line and paste it right here. But we're going to call this one the validation data set. And it's the exact same thing, but this time we're going to change it to false. There we have that. Oh, and the other thing we need is a model. The model equals the linear network train data set. And remember, the reason we're passing it the data set is just so that it can, right here, it takes in the data set, and it is literally just using it to extract the number of channels, the height, and the width. That is literally the only reason we are passing in the data set. The other reason it needs to be on the CUDA is because you can't matrix multiply one thing that's on the GPU and one thing that's on the CPU, right? And we already put all this data on the CUDA. So it needs to be there too. And if you want, we can also put async equals true here as well. Okay, so right now, train data set and validation data set, they're going to return things one at a time. And remember, we defined it to do that right here. It just returns one image, but we don't want to train on one image that's not utilizing the GPU to its fullest extent, right? So what we want to do is we want to train on an entire batch. Well, in Torch, there is this super convenient class called a loader. Train loader equals data loader, and we're going to give the data loader a train data set. We're going to say that the batch size equals 42. We're going to say pin memory equals true. I don't remember exactly what pin memory does. I believe that it makes sure it stays in the same place in memory so that it doesn't have to like be constantly booted out of the cache. I can't remember if that's supposed to be on the GPU or on the CPU or in RAM or where. I can't remember, but you know, it makes it faster with memory somehow, and that's great. We love fast. Okay, and then we're going to do the same thing with a validation loader, data loader, and we're going to pass in the validation data set. And again, we're going to say the batch size is the meaning of life. Okay, so there's our train loader and our validation loader, and that will put things into batches, and most importantly, it will put the batch as the outermost dimension. So there's n batches times C channels times H height times W width. A very important thing I forgot to mention to you guys. For some of you, this async will work, but for most of you, it probably will not, and that is because in most versions of Python, async is a reserved word, and so what you need to do is call non-blocking instead. So let's just change that to non-blocking, and where else did we do that? Non-blocking. Okay, now let's go see if it's done installing stuff. Looks like it's done installing, so let's see if it imports it correctly. Import error, oh no! Ah, indeed. I have an import error because right here I am using Python 2, and I attempted to install it with pip 3. Kernel. Change kernel. Python 3. Well, let's see if it works now. Ah, see? It works. Ta-da! Let's see if this works. Ah, works! Okay, length is missing one required positional argument I. That's funny because length isn't even supposed to have a positional argument, so let's delete that. And I also deleted, by the way, non-blocking thing in here. Validation loader is not defined. Oh, capitalization. Validation lost list is not defined. Okay, let's run it again. Name loop is not defined. What? Indeed, loop is not defined. And so let's define it here. TQDM has no object attribute set descript. Indeed, that is not a function, but that is. Key error, D. Ah. Apparently it's just that. Unsupported format string passed to nonetype.format. What? Okay, I think I found the error. We're going to still leave that as -1, but we're going to have to change this to be append right here as well. So we can delete this and this. Okay, optimizer is not defined. Optimizer is not defined. Optimizer is. There. Now it's started to train. We need to output the stuff that we created. Okay, so let's say fig equals plt.figure x equals fig.add subplot 111 x dot plot the range of the length of the validation losses, We'll label it equals validation loss. And that same thing, but for train losses, label equals training loss. We'll add a legend and let's show it. Yeah, well, that's wrong. Okay, so the problem was that we never even got to epic number 25, so it never went inside this loop. So I'm gonna lower it to 2 epics. You'll be training for a longer time, so you can have it higher at like 5 or 10 or whatever you feel is best. The other thing I'm gonna do is that I'm gonna put this whole thing in parentheses and then call dot item. Same thing here. Okay. There, that's more like it. Okay, this is never really leveling off, but that's because we didn't run it for so many epics. It obviously still has a ton of learning it can do, but I just wanted to show you how that actually works. And this time if we print the tensor, more stuff in it. See? Exactly 5, which is what you would expect for 10 epics. You might want to know how to print out the parameters and mess with those. The number of params is the sum of torch.numl, number of elements in the layer for each layer in model.parameters. So we got a pretty small network, almost 0.7 million, 0.8 million. Okay, I believe that's everything that you need to know for the lab. So good luck and have fun.